All right, so we're going to finish up the second half of section 1.3. Okay, there's a little bit more stuff in that. And then we'll look at what we can of 1.4. You might, you'll find a lot of 1.4 review. It's like y equals mx plus b, slope, parallel lines, perpendicular lines, all stuff you've really done in Algebra 1 and geometry. But we'll go through it, some of it, you know, if we have a little extra time at the end. Okay. So the first thing they mention in this part of the section is what's called the greatest integer function. And it's not a super complicated function. In fact, there's no real even arithmetic to do in the formula for it. It just says that if you give me an integer, I will give you back the biggest integer I can think of that's less than or equal to the integer you gave me. Okay, so we'll try a few examples. What if I said 5? What's the biggest integer you can think of that's less than or equal to 5? Damien? 5, yeah. How about if I said 5.1? What's the biggest integer you can think of, but it has to be less than 5.1? Yeah, 5. How about 5.9? Biggest integer you can think of, but it's got to be less than 5.9. Yeah? 5. This, all of a sudden, if I go from, even if I said 5.999, it's still 5. But then all of a sudden when I say 6, now the answer is 6. So it's like the answer jumps once you go from 5.99999 repeating up to 6. So it gives it a graph that looks kind of like steps. They jump. Okay, and I'll show you an example in a second of a picture. Okay, the symbol for it, you might see these double brackets, or on the graphing calculator, capital INTX. And the graph looks like that. So let's just kind of go through it. If you give me 0, the answer is 0. 0.1, the answer is 0. 0.5, the answer is 0. 0.9, still 0. 0.9 repeating, 0.99999, still 0. Then when you get to 1, let me make it a little bigger. Notice how I put an open circle on 1, because this part is not where you would look to see what's the answer when I hit 1. It jumps. At 1, jumps up to right there. And then it will stay at 1 until you get to 2. And then it jumps up again. So it looks like a set of stairs. How about a negative? What's the greatest integer you can think of that's less than negative 4.1? One thing. Biggest integer you can think of, but it's got to be less than negative 4.1. Yep? Negative 5. So you got to think a little bit, wait, less than means it's like on a number line, it's to the left. So negative 5 is the biggest number that's still less, biggest integer that's less than negative 4.1. Okay. So let's look at how we would graph this on the calculator. I think I mentioned that it looks like a series of steps. So it's also known as a step function. An example where that's used is like when you pay for postage. If you want to mail something that's 12 ounces, there's a fee you would pay, and the fee to mail anything between 12 and 13 ounces up to is the same. So if you want to mail something that weighs 12.5 ounces, same fee. 12.9 ounces, same fee. 13 ounces, it jumps up to the next rate. Okay. So postage scale works like that. There's other things that work like that too. Like tax brackets, maybe if you make between certain money, you pay this, and then all of a sudden you jump up to the next bracket. But there's nothing in between brackets. You're either under 50,000 or you're in the next bracket. You're over 50,000. I'm just making up numbers. Okay, so how do we graph it on the calculator? So find a complete graph. That just means find a window on the calculator that looks good, kind of get the gist of the function. How do we type it in? So what we have to do is go on your calculator, turn it on. You're going to go to y equals. If there's anything in there like I have now, you can just clear it. And we're going to go to math, number, and the fifth option down is int. In my calculator, it's not capital there, but that's fine. We're going to type in int x, and then close the parenthesis just because we had one that was open. Yep, so you're going to go to math, number, and then the fifth one down, int. Okay, and then to make everyone's window look the same, I'll go zoom 6. And there's your greatest integer function. Notice it can't really put the little circles on it. But there really should be a solid circle on the left of every step and an open circle on the right. There it is. Now, they want to know the domain and the range. So domain is what you can plug in. Okay. What kind of numbers can you plug into the greatest integer function? I don't want to know the answer that I get. I just want to know what kind of numbers can I find the greatest integer for. Yeah.
Is it all real numbers?
All numbers, yeah. You can find the greatest integer for a fraction, decimals, positives, negatives, 0. Even pi, something irrational. The greatest integer less than or equal to pi, 3. Yeah.
Don't answer it.
Oh, yeah, 3. Yeah. So you can find the greatest integer function for anything you want. Now the answer that you get, the range part that I just put a box around, that's not any number. What kind of answer do you always get when you use this formula? Yeah? An integer. You'd never get an answer from this graph of like 0.6. The y value is never 0.6. The y value can be 0, it can be 1, it can't be anything in between, up and down. So the range, there's no real fancy way to write it. Just write all integers. Okay. And that's it for the step function. Any questions there? Okay, let's practice domain and range on a different function. It's 16x minus x cubed. Now, I'm sure if I mentioned this last week, this exponent is really important. Does anybody know what that, well, it tells you a few things, but does anybody know visually what that exponent tells you about the graph? Yeah?
Like 3-dimensional?
It's going to be 2D because of the number of variables. So this is going to be a 2-dimensional graph. But, yeah?
The exponent can tell you the number of turning points and what direction the end of the graph goes on times.
Mm-hmm. So if you subtract 1 from the highest exponent, there's only one exponent. I guess if you want to pretend there's a 1 there, but we normally don't write that. If you subtract 1 from the highest exponent, that tells you how many turns the graph could take. Not necessarily will, but it tells you the most that it could take. So this kind of graph can turn twice. What does that mean? It can go up, it can turn down, and it can turn back up. So it could look something like that. In fact, we're going to learn, this is called a polynomial. And if you keep this as any odd number, 3, 5, 7, or 9, the answers that I'm about to write down for domain and range would all stay the same. You could change it to a 5, any odd number you want, and it would not change the answer to this problem. It would change how the graph looks a little bit, but it would not change the domain, and it wouldn't change the range. Maybe let's just keep it as a 3. Okay, so domain is the numbers you are allowed to plug in for x. So remember the two things you can't do. Divide by 0, square roots of negatives. Could either one of those happen here? What do you think, Sebastian? No? You're multiplying a number by 16, and then you're going to cube that same number. You can cube any number you want. Positive, negative, fraction, or decimal. It doesn't matter. So the domain is all reals. In fact, we're going to learn more about polynomials, but this is a polynomial, and the domain of every polynomial is all reals. Always. Okay, let's look at the range. So I'm going to get rid of my step function. 16x minus x cubed. Let's go zoom 6. Okay, so knowing what I know about this graph, I know it's turning. I can't see where it's turning. That's bad. That's not a complete graph. The turning points are off the screen. So what would I have to adjust so I can see more up and down? What two values? Yep, Henry?
The y.
Yep, I'm going to adjust the y's. Now, how much do I have to adjust it? I don't really know. Well, I do from the last class, but normally I wouldn't know. So I'm just going to guess the same thing I did in the last class, negative 35 to 35, and see how that looks. Looks good on the low. Yep, perfect. Okay, so now we can see the graph. We can see both the turns. This graph will never turn again. It's not like there's going to be another turn down here and back up. No, that exponent says that can't happen. It can only turn twice, and there's both. Okay. So how high and low does it look like the graph is going? I mean, we know it's negative 35 to 35. We can see that. But knowing that the graph is never going to turn again, what do you think the highest and lowest is? Yeah?
It just goes on forever.
It goes on forever. That's going to continue up. That's going to continue down. So the range, all real numbers. In fact, any odd degree polynomial, that means any polynomial where the highest exponent is an odd number, these two answers would always be the same. Now, if you're wondering what happens with an even number, let's say you made it x squared, that's a parabola. So now you've created a U shape. Well, with even polynomials, they either go up forever, if it's a U shape, or if you flip it over, it becomes more like an N shape, and then it would go down forever. Okay? So the range can change a little bit depending on if it's an even or an odd exponent in a polynomial, but the domain cannot. It will always be negative infinity or infinity. And if you're not sure, it's like, what's a polynomial? He keeps saying this word. We're going to study more about them in like chapter 2 or 3. Okay, what makes something a polynomial? An example of something that's not a polynomial, square root. Square roots aren't polynomials. And the problem we went over in the homework, like that, that's not a polynomial at all. So we'll talk more about that. Okay, so let's look at this word problem. So we've got a rectangular pool, and the pool is 30 by 50 feet. There's a sidewalk all the way around the pool, and the sidewalk is the same width on every side. We'll call the width x. I'm not going to tell you what the width is, that's what you're going to have to find. But I'll tell you the area of the sidewalk is 600 square feet. Okay, what's the width? So what do you think would be helpful to do with all this information? I mean, we've got all the facts, but I think this problem would be a little easier to tackle if we did what? Yeah?
Wrote it out in an equation.
Okay, write out an equation, and what would help us to make an equation? But that's going to be the whole key. We're going to get an equation. What's going to help us make an equation? Yeah.
If you were to get, like, if you were to define something as y.
Okay, so that's going to have to do once we start making an equation. We'll have to figure out what our variables are. But maybe somebody just reading all these facts, they just see a bunch of facts and it's not an easy way for them to see the problem. There's another way we could represent all this information. Yeah, Katie?
Can you draw it?
Yeah, if we draw it, for some people, it might make it a little easier to see what's going on. So let's start with a pool. There's our pool. And it said the pool, I think it said 30 by 50. Okay, and we'll shade that in blue for the pool. Now we have a sidewalk all the way around it. So let's put a sidewalk. It says the sidewalk is uniform width. Good enough. So there's our sidewalk. And what did it say the width was? They gave us a variable to use. X. Okay, so let's see if we can come up with a formula that would calculate that, because that's the only number that we have besides the dimensions of the pool. So somehow we've got to use that 600. So let's let A sub S be the area of the sidewalk. I can write that out if that's confusing. So area of the sidewalk. From that picture, how would you find the area of the sidewalk using the rectangles in that picture? I think what you could do, you want to get just the sidewalk. So we have really a couple rectangles in that picture. What could we do, Sebastian?
You have to subtract the area of the pool from the area of the total.
Yeah, subtract the area of the pool from the area of, I don't really know what to call it. We'll just call it the area of the large sidewalk. That's the equation we have to set up. Now, if we can fill the right numbers in, then we can find x. Well, area of the sidewalk, 600. We already know that. So that's 600. And the area of the pool, well, we don't know it, but we can find it. The pool's 30 by 50. So what's the area of the pool? Yeah, Joe? 1,500. Very good. And now, since area is length times width, we just have to find the length and the width of the large rectangle. So let's start with the length. How long is that line I just drew in red? Yeah.
50 plus 2x.
Yeah, it's 50. It's this section plus this section plus this section. So 2x plus 50, 50 plus 2x. Now, using the same reasoning, we can get the height. It's 30 plus 2x. Or 2x plus 30. Now we've got an equation, and we've got something to solve. Okay, so let's do this out. Remember what's in the parentheses here, that's FOIL. So you have to distribute that all out. So you're going to get 4x squared plus 60x plus 100x. So it's plus 160x. And then we did this earlier. What's 50 times 30? Yeah, 1,500, but then I'm going to subtract 1,500. So what's going to happen to the 1,500? It just cancels out. So I don't even need to write down plus 1,500 minus 1,500. That just cancels out. Okay, so there's the equation we have to solve. What kind of equation is that? Since the highest exponent is a 2. Yeah.
Well, when you graph it, it would be a parabola.
Okay, the shape of it is a parabola, and parabolas are created from these types of equations. Yep.
Quadratic.
Quadratic, exactly. That's a quadratic equation. So now we have a couple options. We can factor, maybe. We can use quadratic formula. We can complete the square. I'm going to assume people can do quadratic formula from algebra 1. But if you're not familiar, you don't remember, just as a reminder. That's your quadratic formula, where A, B, and C are the numbers in these positions. So the whole key is you have to get it equal to 0. So I'm going to get this equal to 0, but I'm not going to use quadratic formula. I'm going to show you how to do something on the calculator. Okay? But before I do it, quadratic formula is the only way to get the exact answer. What I'm about to show you on the calculator is going to give you a decimal. So if the directions in a test problem said find the exact answer, you've got to use quadratic formula. Okay? All right. How would I get the 600 on the other side? How about Asa? How would I get the 600 on the other side?
Subtracted?
Yeah, let's subtract it. So keep everything else the same. And if you wanted, you can divide everything by 4, just to make all the numbers smaller. At this point, if you're just going to plug it into the calculator, it doesn't really matter. But just because it'll be smaller numbers, I'll do it. Be careful you don't mess up when you do that, because then if you mess up, you've now just ruined the whole problem. So, okay, so now we're going to graph that. I want to know where this graph hits 0. Okay, think of it like that's your y value. If you're trying to find when the y value is 0, what does that mean you're trying to find in the graph? If the y value is 0. Yeah?
Like the x-intercept?
Exactly. We're looking for the x-intercept. So where does this graph cross the x-axis? Okay, let's graph it and find out. So we've got x squared plus 40x plus 40x minus 150. Now, I know from the other class what to set the window at, so I'm going to set my x min to -60, just so you can see something. And I'm going to set the y min at like -200. You don't need to do that. If you want to just do zoom 6, that's fine. Do zoom 6, and then just wait for me for 60 seconds. If you put in the x after the 40, that works a little better, because that's the actual column. I didn't go quite low enough, but that's okay. Hopefully you can get the point that it's a U shape. That's not a complete graph, but I don't really care where it bottoms out. We are going to care about that later today, but not for this problem. All I care about is where it crosses the x-axis. And I see 2 spots. 1, 2. Now remember, x is the width of the sidewalk. So let's look at this first answer on the left. Any thoughts about that answer? Yeah?
It's not a valid answer.
It's not a valid answer.
Because it's like you can't have a negative width.
Yeah, you can't have a negative sidewalk width. So although mathematically I can find a negative number for x that would make this 0, in the word problem, it doesn't make sense. So I'm just going to focus on the answer that's on the right, which, if you did zoom 6, you're fine, you're already there. Or if you have this window, that's fine too. You can use either one.
What did you set your windows for again?
Negative 60, and on the x min, x max is 10. The y min I did negative 200, but that's not really necessary. But you could do it. And the y max was 35. So now what I'm going to do is second calc, and the second option is 0. Okay. A 0 is used to find where a graph crosses the x-axis. So the way this works is you have to pick a point somewhere to the left of where it crosses the axis, to the right, and then do a guess. So I can see right now that I'm at negative 25, and I'm at negative 500, so I'm way, way down. I'm going to start moving to the right. And as I move to the right, you're going to see this negative number start to head back up on the y values, eventually. All right, so it's coming back up. And I think my window goes from negative 200. So when I hit negative 200, you'll start to see it. There it is right there. So you have to pick a point that's somewhere to the left of this spot. Where I am right now is perfect. So I'm just going to hit enter. And what it did, it's a little hard to see, but it put in this dotted line. That means it's going to look between the dotted line on the left, and now I need to put in another dotted line. So now keep traveling to the right until that y value is positive. Okay, so keep going. You can go off the screen if you want to, that's fine. But I just hit enter, and it put in another dotted line. So now my calculator is looking between those two dotted lines to try to find that point. Now, it only crosses the x-axis once, in between the dotted lines. So the guess isn't really important. You put the guess wherever you want. And when you hit enter, it finally gives us the answer to the problem. This crosses the x-axis at 3.45. And that's in feet. Okay, so that's the value for the width of the sidewalk. Does anybody need the work that was underneath? I can move this stuff if you need it. Okay. Solving that. I would just round it to 3.45 feet. If you use the quadratic formula, that might be a good way to review if you don't remember it. Use it and see if you get 3.45. And when you do plus or minus the square root, you'll also get the negative answer as well. But again, that doesn't make sense. Any questions on how we calculated a 0 on the calculator? Yep.
What button did you press again?
To get to the 0,
Yeah.
second, calculate, and then the second option down is 0. If you don't pick a point to the left and to the right, let's mess up. That's to the right. I should have been to the left. So let's see what happens now. It's probably going to say error sign change. No sign change, meaning you never crossed 0. Okay, the whole point of it is you got to make sure you pick a number that's below 0 on the y value, and then above 0 on the y value. If you pick a number above and below, or below and above, depends on which way the graph is going, you'll always get 0 trapped right between those dotted lines. And then the guess doesn't matter.
Okay, so how do you put the dotted lines on after that?
You just pick a point to the left and you hit enter, and then you pick a point to the right and you hit enter. Because it'll say left bound, right bound. So if your graph looked more like this, so your graph looked like this. You wanted to find this spot right here. Well, the first thing you're going to do when you pick a point to the left is it's going to be above 0. And then when you pick a point to the right, that one will be below 0. And then you'll have trapped 0 between the two. Okay, and I think it puts a little like shaded arrow right there, so it knows, kind of tells you which direction it's looking. I don't know if I saved that picture or not. I might have. I think it's one of the pictures under here. Yeah, right there. It was there. Right there. Okay. So that's how you calculate a zero. Okay, any other questions on that? All right, some of it you just have to kind of practice and play with it and get used to doing it. Okay, so projectile motion. So this is the simplified equation. It doesn't really take into account some real-world factors. So if you tried this in real life, it might not work exact. But it's a simplified version of projectile motion, which basically means you take an object, you throw it. It doesn't have like a motor on it. It's not like a rocket. You just throw it like a ball, and it goes up to a certain height, and then it comes back down. And there's a couple things that will affect how high it goes or how long it's in the air for. One is how hard you throw it or launch it. So V sub 0 is initial velocity. And S sub 0 is an initial height. Okay? It makes a big difference if you're standing on the ground and you throw a ball, or you stand on top of a building and throw the ball off the building. Well, if you've got an initial height and you're standing on top of a building, it's going to take a lot longer to come back down. T is the time. So you might want to know how high is the ball 3 seconds after I throw it, 5 seconds, things like that. And S sub t is your height. Now in physics, you might see a different formula for projectile motion. And that could depend on the units. We're using feet. In physics, you usually use metric system. So this formula would look a little different. Yeah.
Is that V sub 0t and S sub 0?
Yep. V sub 0 is your initial velocity, and S sub 0 is your initial height. Now, if they say you're throwing an object from ground level, then initial height is 0, and you don't need it. Most things that you would throw yourself are not thrown from ground level, because when you throw something and release it, you're releasing it at whatever height your arm is at. You're not on the ground when you're releasing it. Your arm is up, maybe 5, 6 feet, depending. Okay, so let's use that formula to figure out this problem. So we're shooting a rocket straight up with from ground level, and the initial speed of the rocket is 64 feet per second. Looks like a 9, but that's a 4. 64 feet per second. So I want to know when this object is going to hit 50 feet exactly. What time does it hit 50 feet at? Now, if you're firing an object from ground level, assuming that the rocket goes higher than 50 feet, how many times will it hit 50 feet? Okay? Twice. It's going to hit it on the way up and on the way back down. As long as 50 feet wasn't the maximum, then it would hit it once. But this is going to go higher than 50 feet. Okay. So what we're basically going to do is figure out an equation that models the motion of for the height of the rocket. We're going to draw a line at 50 feet. Then we're going to find the two spots where it hits 50 feet. So we're going to calculate an intercept. Okay, so let's set up our equation. Our height as a function of time is negative 16 t squared plus v sub 0 t. What's my initial velocity? Brandon? Yep, very good. Plus my initial height. What's my initial height in this problem? Yeah, Jacob?
0.
0. So I don't need to put an initial height. So the question is, when do we hit 50? So we're going to graph 50. We're going to graph negative 16x squared plus 64x and see where they cross. Remember, for the variable in the calculator, you always have to use x. So let's put in a line at 50. Negative 16x squared plus 64x. Now, I don't know how high the rocket's going to go, so I'm going to guess it doesn't go over 90 feet. If it goes higher than that, I'll have to adjust it. But let's just set our Ymax at 90 feet. Now, if y is the height of the rocket, does negative 200 make sense? Not unless the rocket is drilling into the ground, so it's not happening. X is time, so unless you're Biff or Marty, it's negative doesn't make sense. Anyone catch that reference? Back to the Future. Okay, moving on. So negative time doesn't make sense. And then x max would have to be, well, we don't know how long it's in the air for. So I'm going to guess that it's not in the air more than 10 seconds. So there's my 50-foot mark. Here's my path of the rocket. Yeah, good enough. So we're going to calculate 2 intersects. And those are the times when the rocket hits 50 feet. Second, calc, intersect. Pick a point on the blue. Pick a point somewhere on the red. Doesn't matter where. I just had to keep hitting left till I got back on the screen. Mine was off the screen. Now the guess. Is the guess important? This time it's very important. Because wherever I put my guess closer to, that's the intersection point it'll give me. So there's 2 of them. I'll do the one on the right. If someone else can do the one on the left, then we'll have both. Of course, another way to get the other point is if you know the time that the maximum value occurs, the 2 times I'm looking for are symmetrically spaced around that number. So if the maximum time was, to me it looks like it's almost 2 seconds. Well, this is 0.93 seconds after 2. The other answer is going to be 0.93 seconds before. But you don't need to know that. You can just calculate the intersect and figure it out that way. So 2.94 seconds. And does anybody have the other intersection? Yep.
1.06 seconds.
1.06. So I told you 0.94 seconds after, 0.94 seconds before. So technically, if you average those 2 numbers, it'll tell you exactly when the maximum height is. It is at 2 seconds. That's actually the next question. Well, part of the next question. So the next question asks, what's the max height and when does it occur? Well, let's say I hadn't told you it was 2 seconds. What you can do is undercalculate. Okay, we've done 0, we've done intersect. There's another one here that's option 4. That's maximum. Okay, if you go down to maximum, and you have to make sure you're on the red curve. Right now, I'm on the blue. I don't want to find the maximum of the blue. I could delete the blue if I wanted. So I'm going to press up. Now I can see I'm on the red. So you've got to give the calculator an idea where the maximum is. So first, it says left bound. Pick a point that's to the left of the maximum and hit enter. Right bound. Pick a point that's to the right of the maximum and hit enter. Now, the guess isn't really important because there's only one maximum in between the dotted lines. So hit enter, and then you get the maximum. It says that the maximum is 2. Well, the 2 is the time, and 64 is the height. So max height equals 64 feet, and this occurs at 2 seconds. So what is it? When is it? Any questions on that? Okay, so that's how you can calculate a maximum. A little harder to calculate a maximum algebraically. Without the calculator, you can use calculus to do it, but that's not something we get into. All right, so the last thing is in this section, and then we'll do a really quick review of like slope, y-intercept, and that kind of stuff. But before that, this is called a piecewise defined function. It's probably easier if I put the example up at the same time. So a piecewise defined function says, okay, there's 2 formulas. You use one formula for certain x values. You use a different x formula for other x values. So this piecewise function is broken up into 2 pieces. Use the first formula for any values less than 1. Use the second formula if you have a value greater than or equal to 1. And you could split it up into 3 pieces. But this one is 2. So what a piecewise function is it's really like taking part of one graph, part of another graph, and drawing them together at the same time. So what I really want to show you is how to do this on the calculator. To do it on the calculator, it's really very similar to how we've been typing things in all along. The only extra step is, well, you got to type in this condition, and you have to use parentheses, okay, around everything. So I'm going to start by typing 3 minus x squared, but you have to put it in parentheses, just like this. And then next to it, you're going to tell the calculator, only draw that when x is less than 1. So I haven't shown you where the less than, okay, where your inequality symbols are. They are under second math. Okay, that brings you to second test. And I want number 5. We're going to go back and do an inequality again if you need to see it again.
Wait, what was the second math in there still?
Second math is to get an inequality symbol. So let's type it in the bottom one. In parentheses, x cubed minus 4x, close parenthesis because you're done with the expression, open parenthesis for the condition of when to use that. You only want to use that when x is greater than or equal to 1. Okay, so the condition here is when x second math, and I want greater than or equal, option 4 and 1. That's how you type in a piecewise function. Okay? You just have to use parentheses. Okay. I didn't hit graph yet, but any questions on that? Now the calculator can't draw it perfectly. It can do pretty good, but it's not perfect. So first of all, if I hit graph, that's a pretty lousy graph. Let's go zoom 6. I can't even tell what's really happening there. Okay, so there's my first graph, but notice all of a sudden it just stopped at 1. That's because the first graph only goes up to 1. And the second graph picks up at 1. Okay, the way that this should really look is, let me show you. The blue and red line on the axis shouldn't be there. This should just be black. With these calculators, I don't know how to make it not do that. I can't. All right? So that part looks good. You've got the blue and the red. The blue, just to be clear, color code it. That's the blue. That's the red. Now, the other thing it should do is this. And see if you can tell me why. It should do that and that. Anybody tell me why? I zoomed out so you can't see it as well, but I need to zoom back in. Why did I put an open circle on the blue and a closed circle on the red? Yeah, Joe?
The first one's like less than, and the second one's greater than or equal to.
Exactly. If it has a less than, when you hit 1, you're not on the blue graph anymore. So you should not include the endpoint of the blue graph. Okay. Small detail, but kind of important. Okay, questions on that? So that's a piecewise function. It's just two graphs drawn at the same time. Maybe they connect, maybe they don't. This one, they don't connect. Okay. Any questions on piecewise? All right, so with the last 10 minutes, I'm going to quickly go through some Algebra 1 stuff. Most of it, I think you're already going to know, so you don't have to write it down. And I'm not really going to leave it up there on the board very long. So if you want to, you can always go back in the video or look it up in your book. Okay, the first thing is y equals mx plus b. Okay, that's a linear function. Anything that you can write in the form y equals mx plus b is a straight line. M is your slope. B is your y-intercept. Now remember, b can be anything you want. Positive, negative fraction, or decimal. M can be almost anything you want. In order for something to be a linear function, m can't be 0. If m is 0, you just wiped out this whole part, and now you have a constant equation, like y equals 2, y equals 6. Okay? You've got to have a slope that's not 0 to have a linear function. I'm going to skip over that. So slope, okay, formula for slope is rise over run, and it's up right there. Yeah. So to find rise over run, subtract your y values, and then divide it by and subtract your x values in the same order. Okay, so I'm sure you guys have calculated slope before. There's two special slopes. If you have a horizontal line, that has a slope of 0. If you have a vertical line, that's an undefined slope. So those are the only two special cases with slope. Everything else is on an angle. And again, so I'll be in the video. So if they ask you to find the equation of a horizontal or vertical line, that's a little different than y equals mx plus b. It's actually easier. Horizontal line is just y equals a number. So in this case, we've done that a couple times. I think we graphed like y equals 50 to get the height of the rocket, or whatever it was at 50 feet. So our calculator can graph horizontal lines. What the calculator can't do is a vertical line. That's a vertical line at 2. X equals 2. Can't draw it on the calculator, but it would go right through the point 2, 3. Okay, so those are two special cases. Everything else is on a diagonal. That's y equals mx plus b. So sometimes you're given something that's not in y equals mx plus b. You should know how to rewrite it, kind of like doing something like this. And and then reducing. So y equals negative 2/3 x plus 2. And the advantage to taking something that's not like this and putting it in y equals mx plus b makes it easier to graph. You can see your slope, and you can also see your y-intercept. You can't tell that when it's written in the form that's in the red box. Point-slop form is another way to write the equation of a line. I don't really use it a ton, but you can. So if you have a problem where they give you a point and a slope, you could fill it into this formula and use that. I tend to use y equals mx plus b for everything. That's how I do it. But if you want to use point slope, you can use that as well. So in a problem like this, what you'd do is you'd fill in 1/2 for the m, negative 2 would be x1, and 3 would be y1. Just fill in those three numbers in those three spots, and there's your equation. And if you want, you'll get an equation. It might look something like this. You can rewrite it. Okay? Rewrite it in y equals mx plus b. Right? Point-slop form, just another equation of a line. General form we don't really use very much. I'm just showing it to you in case you ever see it. Not something you really need to worry about. It's basically just getting it equal to 0. So we tend to do that with quadratics, not as much with lines. I kind of like y equals mx plus b the best out of all of them. That's just a third form. All right, so parallel and perpendicular lines. Two lines are parallel if they have the same slope, but they have to have different y-intercepts. If two lines have the same slope and same intercept, they wouldn't be parallel. What would they be? Yeah? That's the same line. So you got to have same slope, different y-intercept. For perpendicular, you have to have slopes that are opposite reciprocals. People seen that one before? Opposite reciprocals. So that would be something like y equals 2/3 x plus 6, negative 3/2 x minus 8. The plus 6 and minus 8 don't have anything to do with the problem. 2/3, negative 3/2. Opposite reciprocal. So, a problem you might see is something like this. Write an equation of a line that's parallel to this and goes through a certain point. Well, first thing I would have to do is take this and figure out what's the slope there. So I might want to rewrite it in y equals mx plus b. Then once I have the slope, I'll have the m. I've got an x right there, and I've got a y, negative 2. I have m, x, and y. The only thing I don't have is what letter? Robinson?
B.
B. And B is the only thing I don't have. So I just plug those into y equals mx plus b and find b. Now, the only extra step would be if it said perpendicular, you'd find the slope of what's circled, but then you would make it the opposite reciprocal. Okay, but we can practice one tomorrow if we need to. I think that would, yeah, this is going to be the last thing. So the last thing is a linear inequality. I'll do this one real quick because it'll only take me 60 seconds. But when you graph a linear inequality, there's two types of lines, solid and dotted, or dashed. If you have the equal to, you use a solid line. If you don't, you use a dotted line. So if I wanted to graph this one, first thing I would do is just get y by itself. So subtract the 2x, and then divide everything by what I divide by. Sergio?
Sorry.
What would I divide by to get y by itself?
3.
3. So what I end up with is this. Kind of a messy problem to graph, but that's the way it goes. So my y-intercept is 4/3. 4/3 is about 1.3. And then I need to go down 2, right 3. Down 2, right 3. And do it one more time. Down 2, right 3. Now, we're going to make a line there. In this particular problem, it would be dotted. So put in dotted line. And that's okay, I can fix that. So make it dotted. And then once you put in a solid or a dotted line, you basically just shade. Well, the easy way to figure out which way to shade, less than, shade below. Greater than, shade above. It's the simplest way to explain it. This is a less than, so I shade everything below. That's it. Okay. How many people have done that kind of stuff before? Dotted, solid. Okay. So again, if this was all new material, we definitely would not go through it that quick. But I'm assuming slope y equals mx plus b, you've done all that. So we can't really spend a whole 2 or 3 days on y equals mx plus b like algebra. Okay. Alright, so homework tonight, page 31 is the end of section 1.3, and page 42 is 1.4. Again, I'm going to put that all online, but if you need any of the notes from anything we went through in the last, especially the last section, you'll have it. Remember, some problems are calculated, so if you come across a calculator one, it might be nothing to write down. Yeah, Rob?
Can I take a picture of it?
Yeah, sure, you can take a picture. Just make sure if you take a picture, no one else, including me, is in it. Thank you.